sign.
Yes.
అది ల్యాప్టాప్ కనెక్ట్ చేసి హెచ్డిఎంఐ ప్రొజెక్టర్ అది ప్రోగ్రామింగ్ చూపిస్తుంది.
Computer, maybe you can try this.
సాయి 205 ల్యాప్టాప్ ది స్క్రీన్ పైన డిస్ప్లే స్క్రీన్ లో వస్తుంది, ప్రొజెక్టర్ రావట్లేదు. న్యూ షూర్ ఒక్క నిమిషం. అడ్వాన్స్ స్క్రీన్ అని చూపిస్తుంది. అడ్వాన్స్ లో పోవాలా ఫస్ట్? అడ్వాన్స్ అని కొట్టి 2 సెకండ్ కన్నా కొట్టాలా? వచ్చింది ఆల్రెడీ. ఓకే ఓకే, కనెక్ట్ షేర్ కొట్టాలా? ఓకే, ఇట్స్ ఓకే. ఓకే సాయి వచ్చింది.
Yeah, I can.
Sir, can you one check once?
It's 100%.
Okay.
Was it supposed? Oh, yeah, okay, that's I just took it. I just took it without even asking. Yeah, that should be. No, but keynote is not very good with these. Yeah, you want? No, I can choose. No, no, that's okay. It's better. Right.
It's okay. No, no.
Then you switch to camera.
Yeah.
You know, I think let me start. Oh, that guy came and did something I forgot. Oh, yeah. Okay. Yeah.
What kind of process? You
No.
not effects. You know, I don't know.
No, it's not instruction.
Happening only on Zoom.
I don't know.
No, it's happening only on this.
Okay, it's not happening on my end, definitely.
Yeah. Okay. Try changing this thing.
Yeah.
Welcome everyone to the session B6. This is a session on counter automata. The first talk will be given by Kushraj Madani on counter machines with infrequent reversals. Over to you, Kushraj.
So, do I need a mic or no? I think I need it. Yeah. Oh, yeah. Thank you. So,
And keep it, that's.
that's okay. Yeah. So, good afternoon, everyone. I'm Khushraj Madnani. Thank you for the introduction. Uh, and I'm going to talk about counter machines with infrequent reversals. This is a joint work with Ala Finkel, Shankaranaran Krishna, Rupak Majumdar, and Georg Zatsche. First start with some preliminary definitions, followed by explaining the notion of infrequent reversals that we introduce in this paper, and then finally we will discuss our main results. So counter machines. Counter machine is a four tuple dq delta q0, where C1 to which contains C1 to CD counter variables that can take non-negative integer values. It has finite set of control states and an initial state, initial control state, and transitions amongst these control states, which are labeled by a vector of dimension d, but vector over integers, which basically encodes how do you change or how do you increment or decrement the counters C1 to CD when you take that transition, or it can have some zero tests, which basically indicates when this transition can be taken. So I'll just explain the semantics of counter machines with an example, with a very small example. So first of all, the configuration of a configuration of a counter machine is a tuple containing a control state and the value of all the counters. And the initial configuration is Q0, that is the initial state, control state, comma, all the counters set to 0. So let's see how does a run of a counter machine looks like. So the run of a counter machine is just a sequence of its configurations, starting with the initial configuration. Suppose consider this counter automaton or counter machine with two counters C1, C2. Now from Q0, you can take two transitions, either the purple one or the yellow ones, because you cannot decrement beyond 0 or below 0. So suppose you take the purple transition for n times. So in that case, what happens is this transition increments both C1 and C2 synchronously by 1. So I mean, if you take this n times, you'll reach Q0 n comma n. And then finally, you can now, I mean, if you now plan to switch, you cannot take the yellow transition because C1 is no more 0. And now you take this white loop, which basically decrements C1 by 1 while incrementing C2 by 2. So something like this happens. And finally, when C1 hits 0, you can choose to take the yellow transition and reach Q2 state. So this is one of the valid runs of this automaton, where you reach Q2 0 3n, where n is the number of times you took the purple transition in the first iteration. And a point in a run where one or more counters switch from incremental mode to decremental mode is known as reversal. So it's a very informal definition of reversal. For example, in our case, this was the point where C1 shifted from incremental mode to decremental mode, and there is no other point where any other counter shifted their modes. So since this is a reversal, and the example run that we considered was indeed a one reversal run. That means you had exactly one reversal point. So a vector addition system with states is nothing but a counter machine with where you are restricted to not use the zero tests. So you can either increment or decrement a counter on an edge. So the reachability problem basically asks, given a counter machine CM and a configuration C of a CM, can you reach the final can you reach this configuration C from the initial configuration? And this problem is in general undecidable for counter machines. For vector addition systems, it becomes decidable, but the complexity is very, very high. That's Ackermann hard. Hence, various restrictions on these both these models were studied in the literature to get a tractable complexity class for reachability problems and other relevant problems. So one of the prominent restriction was reversal bounded, studied by Ibarra in 80s, and counter machine or a VAS is called reversal bounded if and only if all its runs or k reversal bound if and only if all its runs are k reversal bound, or it has at most k reversals. And reachability for reversal bounded counter machine becomes desirable, and correspondingly the complexity of reachability for VAS drops to NP complete. So it makes sense to kind of generalize this notion and see whether we can get larger classes or larger coverability with probably the same results. And so we thought of something called as notion of infrequent reversals, where we do not bound the reversals, but let's see what we do. So given a counter machine CM and or a vector addition system CM and a monotone function from naturals to naturals, we say that a CM is F reversal bounded if and only if for any run R, any of its run R, the number of reversals that R can contain is bounded by F of the length of R. That's it. So in some sense, you are not bounding the with a common constant. You're bounding basically as a function of some length of the run. And notice that every machine is F reversal bounded for identity function, right? Because you can have at most n reversals in n+1 run. N+1 length run. So that's it. So it's important. I mean, so and moreover, we also say that F is essentially bounded if for counter machines or VAS, if and only if for any F reversal bounded counter machine CM, the counter machine is also that given counter machine is also constant reversal bounded. So in some sense, that F grows so slow that the corresponding counter machine is indeed a constant reversal bounded counter machine. So now the decision problems that we are interested in is the following. It's basically we are interested in the reachability of F reversal bounded counter machines and F reversal bounded VAS for the class of functions that you can think of. Basically, where F is one of the inputs of the. So in some sense, the input is a F reversal bounded counter machine and a configuration C, and output is basically where you check whether you can reach the C in this one. So in some sense, notice that this is a promise problem. In some, the counter machine is given to us is along with the promise that it is indeed an F reversal bounded counter machine. So yeah, now yeah. Exactly, yeah. 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 Yeah.
How do you say that? No.
No, the function is called essentially bounded. If basically in some sense, if bounding it with an F bound, indeed results in a machine which is indeed a constant reversal bounded. Function is not bounded, but the resulting VAS actually results in a constant bound counter machine. So in some sense, it will be clear what do I mean later. So yeah, so main results, and I think here it will be clear. So in some sense, what does it mean? So suppose F is any function from end to end, monotone function from end to end, and F is essentially bounded for counter machines, or F grows as fast as logarithmic function. So here, for example, if you take F log n, so in some sense, so what do we prove is in some sense, if you take any F which grows lower than slower than log, it will basically result in a counter machine which is indeed a constant counter machine, reversal bound counter machine. So in some sense, there does not exist a log reversal bounded counter machine in the real sense, right? So that's basically the main result. That and if F belongs to omega log n, that means if F grows as fast as log n, then reach F, that means the reachability problem for F reversal bounded counter machines becomes undecidable. So reach F is undecidable. So and we have the same dichotomy for VASes, but for VASes, the functions basically saturate at linear itself. So either you have linearly many reversals, or you have constant bounded VAS. So there is nothing in between in some sense. So in this presentation, I'll be focusing on the first part. And we'll first start with 1.2. It's relatively easier. So remark that if you have, if reach f is desirable, if and only if reach of b into b times f is desirable for some constant b. Why? Because if I have a counter machine CM which is reach b times f reversal bounded, then what I can do is I can consider CM prime, where what I'll do is from every transition Qi, INST Qj, I'll add these dummy transitions which does not affect any counters, that is Qi0 to Qib. And then I'll basically do Qib, INST Qj0. And that should suffice. Why? Because now any run, and for every run of length L with K reversals in the actual in CM, I have an equivalent run of B times L in the later with same reversals, because I'm not changing any counter values. Sorry. So this is basically this is very trivial result in some sense, that the constants do not affect. You can always simulate with these kinds. So now you can have elongated the runs. You have kind of pushed some dummy transitions to make sure that the number of reversals are f by b in this case. So hence 2.2 is straightforward. So this also holds for VASes. So for 2.2 it's straightforward. Like, I mean, if you have a linear VAS, any VAS is an n reversal bounded VAS. That was clear, right? Now, if you have n reversal bounded VAS, that could be simulated by n by c reversal bounded VAS for any c, and hence you get Ackermann hard complexity for these class of functions. So now, moreover, for 1.2, we just need to show that reach of b into log is undesirable for some constant b. That's all it is. So, but this is not as trivial as before, because in some sense, unlike before, we need to push, we need to kind of, the number of dummy transitions that we need to add between these two transitions, between this Qi and Qj, is actually dependent on the history of the run, right? Because every time the length of the run increases, you want to add more and more dummy transitions. You want to enforce more and more longer runs. Hence, this is no more a constant. So we need to pump exponentially long runs with polynomially many reversals. That's basically the trick. To do this, we basically construct this gadget. Now, this gadget is very straightforward. In some sense, it uses 4 auxiliary counters, A, B, C, and D. And notice these rectangle paths. So in some sense, the moment you enter Q2, the next time you exit Q2, A turns to 0 and B turns to twice the old value of A. Symmetrically, whenever you exit Q5, A turns to twice the old value of B, which means 4 times the old value of A when it entered this previous rectangular box, and B ends up with 0 value. And this, what does this do? This does nothing but, because you're adding first and then subtracting, this basically changes C to D plus 1. That's it. And D changes D to 0. Sorry. Now notice the following. Oh, can I use this pointer? So now notice the following. If my counters are T0, S0, right? In some sense, the number of times I'm basically looping over these two boxes is exactly the number of times the value of C, which is S. So I'm actually multiplying A with 4 S times. Hence, the value of A will be 4 into S times T. Moreover, here when I'm decrementing C, I'm incrementing D. So I'm actually storing the old value of C, and then I'm decrementing C just by 1. Incrementing C just by 1. The value of new value of C is S plus 1. So in some sense, the C stores the length of the number of instructions that has been simulated till now, and A basically helps to pump exponentially long runs. Moreover, look at the number of reversals. Here, you can have at most 1 reversal. So 1 entry and 1 exit will give you 1 reversal. Same is the case here, same is the case here, right? So you can have at most S twice into S plus 1 reversals, which is order of S reversals. So you have linearly many reversals. And so this is basically the idea. A finer analysis is done in the paper, but this is basically the overall idea. Now, the more interesting part is this, that if F is essentially bounded for counter machines, if F is slower than logarithmic, grow slower than log of n. So how do we prove this? For proving this, we basically need the tools from Presburger arithmetic and semilinear sets. And I'll just quickly go over these formalisms. So Presburger arithmetic is nothing but the first order theory of integers with addition less than and equal to, and they have the usual meaning over the integers. And then you can have terms which are variables, constants, and of course you can add them. And your first order formulas, or first order quantifiers, and Boolean operators. It's very trivial kind of this. Syntactically, it's very trivial, but of course it has very interesting properties. And you can write properties like this. So phi of y, what does phi of y say? There exists x, y is equal to x plus x, which basically says that, defines a set of all the even numbers. So semilinear sets. So what are linear sets? Linear sets is a subset of ZD, which is Z is the set of integers, and it's said to be linear if and only if it can be represented in the following form. There is V plus all the linear combinations of V1 to Vm, where V1 to Vm are given are fixed vectors which are given to you. And notice that this strictly generalizes the arithmetic progression, because if m is equal to 1, you get AP. Right? And semilinear sets are nothing but finite union of linear sets. And a well-known result basically shows that Presburger definable sets are precisely the class of semilinear sets. Or because of the quantified elimination, because Presburger admits quantifier elimination, quantifier-free Presburger definable sets are precisely this class of semilinear sets. Right? And the definitions above can also be referred to relations, which is sets. And now basically we start with the proof sketch. So consider any counter machine CM dq delta q1. This is not q0, just notice that. And which is f reversal bounded, but not constant reversal bounded. And let q is equal to q1 to qn, which basically you arbitrarily order your sets. So give a total order to your control states. And now it suffices to show that for k belongs to n, there exists a run of CM with k reversals whose length is at most b raised to k for some constant b. Because if this happens, it will violate the constraint that you have it's an f reversal bounded where f grows lower than logarithm. Oh, yeah. So because because there will be at least one run, that is this run, for which the number of reversals is logarithmic in the logarithm in the so the length of the run is logarithm. So the number of reversals logarithm in the length. Right, so this is done. So without loss of generality, CM has a special counter storing the length of the run. We can assume that. We can have a counter which you increment at every position. And now it suffices to show that for any k belongs to n, there is a configuration Ck reachable after k reversals, such that for all of its counters are less than or equal to bk. So instead of arguing about the length of the run, we now argue about the size of the counters, or the value of the counters, bound on the value of the counters. So now the easy part is done. Now, okay. So the first step is to construct RCM, which is nothing but a relation such that IUJV belongs to RCM if and only if QI from QIU to QJB, there is a path with exactly one reversal, and that reversal also happens exactly at the last point. So in some sense, from QIU, after exactly one reversal, right? After the first reversal, you will reach at QJB. If that happens, so in some sense, you basically define RCM which defines this relation. Now, reachability set of constant reversal bounded machines are semilinear. This was already done by Bara in 80s. Using this, we prove that RCM is indeed a semilinear relation. Once you have this, from now onwards, we will abuse the notation by writing QIU, QJV belongs to RCM. So in some sense, we'll assume that RCM is basically a relation between configurations rather than these numbers. Right? Now, let C0 be the initial configuration. Now, for any k belongs to n, a configuration Ck is reachable after kth reversal if and only if C0 Ck is RCM K. So there is K-fold composition of RCM, right? This is also clear, right? Because C1 is the first, after the first reversal, C2 is after the second reversal, and so on. So which is the first reversal of C1 and so on. Right? So now in step 3, we just need to show that RCMK consists of pair C0 Ck, right? Such that all the counter values of Ck are at most B raised to K. That's all you need to show. At least one of the Ck's is such that. Now to show that, assume that consider a set S or a relation S, which basically maps initial configuration to all the configurations. So basically, it's just the product C0C. In some sense, notice that the second tuple of RCMK intersection S stores the configuration reachable after kth reversal from the initial configuration. So the purpose of S is nothing but to make sure that RCMK only considers pairs. We only consider pairs which starts from runs which starts from initial configuration. That's it. So once we have this, so we now we only need to analyze runs of counters of RCM intersection K, right? And notice that RCM and S both are semi-linear, so you can actually define a Presburger formula. You can actually define the Presburger formula, which characterizes these RCM, both these relations, and this phi R and phi S are just Boolean combination of linear Diophantine inequalities. And hence, if you write in DNF, you can write in this form, where AI is a matrix and BJ is also all matrices, right? And it's just inequalities. So notice that RCM intersection S contains CC prime if phi R CC prime and phi S CC prime, which is equivalent to say that you can pick I and J such that AI BJ, and there is a solution, CC prime is a solution of this particular, right? Similarly, for CC prime being RCM2 intersection S, you can pick I1, I2 such that AI1, AI2, there is an overlapping block of D. And X0 is equal to C and X2 is equal to C prime is a projection of one of the solutions of this equation, where BJ1 and BJ2 is BJ that we picked up. Similarly, we basically iterate this blocks of semi-linear sets, and we get this particular equation. So a C prime is in K, or X0, where X0 is equal to C and Xk is equal to C prime is a projection of this solutions of this equation. Now at this juncture, we basically apply the Potier's bound on the solutions of the linear Diophantine equations, which says that if you have a equation AX less than equal to small a, right, where capital A is the matrix and small a is the vector, the infinity norm of X, that means if there exists a solution, then there exists a solution with infinite norm of X less than equal to this constant raised to m, where this constant is nothing but 2 plus a 1 infinity norm and a infinity norm. So a infinity norm of a vector is nothing but the max of all its contents, and a1 infinity is nothing but max of sum of all the rows. So max of a1, a11, a12 plus a1n and so on. So now notice that we have exactly the same setting, and also notice that ACO1 infinity, basic ACO1 infinity is only dependent on the phi R and phi S. Similarly, A infinity, that is the right hand side, the coefficient matrix, the 1 infinity norm of coefficient matrix only depends on the only depends on the phi R and phi S, and similarly A infinity also, the right hand side infinity norm is also dependent on this. Hence, you have a upper bound on this which is independent of the run that you choose, or of this K. And hence what you get is a bound for X0 to Xk, the solution. So that if there is a solution, there exists a solution where, or if you consider the counters X0 to Xk, all these counters are bounded by B raised to K, because max is bounded by B raised to K, because infinity norm is just nothing but the max of this. And hence you are done. So conclusion, we give a dichotomy theorem for a natural notion of infrequent reversals. Our results imply that reversal boundedness cannot be extended in this way to get larger classes of decidabilities. And finally, the undecidability only holds for the log thing with 6 counters or more. What happens with less counters? We don't know. And can we extend, as a future work, can we extend this notion to other richer, restrictions like infrequent context switches and whatnot? That's it. Thank you.
Thank you, Kushraj. Questions?
So the last part was dense, so I will ask
Yeah,
a
sure.
technical question here.
Sure.
Can you point to us where if the function f is super logarithmic, then something will go wrong?
Well, the idea is what we show here is basically that indeed if okay. In some sense, if function f is super logarithmic, then you will not have this kind of bound. Where do I have? Okay. Then you can never have this kind of bound. Why? Because in some sense, having this kind of bound would mean that function. No, what? So
Yeah, that's the question.
Sublogarithmic, right? Not super logarithmic.
Super log, like when
The problem happens when if the theorem says that if you have a sublogarithmic function, that you indeed have a constant reversal bounded countermotion.
Yes. So where is b raised to k coming from?
B raised to k.
Yeah.
So b raised to k is coming from this. No, so I don't get it. So k is basically the number of reversals that you assume. Right? So you're assuming this set of runs with k reversals.
Okay.
And you say that if you consider the set of runs with k reversals, you will find at least one run whose length is less than or equal to b raised to k. If that is the case, then if you look at the relation between the length of the run and the reversals, there is at least one run where the reversal is less than or equal to log to the base b of k of the r. Right? So your question was what happens if it's a sublogarithmic, right? Where does this go wrong? Right? If it's a sublogarithmic, then you will not have this b raised to k thing, because if it has, then of course it's not sublogarithmic. In which case, this particular matrix will not have a solution.
Another question.
Yeah.
So in complexity theory, it's known that Turing machines which use log n space are essentially equivalent to
Right.
finite automata.
Right.
And your result is very reminiscent of that.
I think we discussed this.
Yeah, so yeah, I mean.
So in my opinion, I have not seen that result. No,
Okay.
and I have to look at the proof to see the correspondence. But I think the main thing here is we are basically bounding the reversals rather than the space of the tape.
But you see, yes, I understand the result.
And I would say that, in fact, what would be more connected to Turing machine would be if you have a two-way Turing. If you basically have a reversal bounded Turing tape in that sense, in the sense that the number of times you can go back in this Turing tape is bounded. So maybe that is connected to the two counter version of this, is what I basically, at least my intuition says.
Makes sense. Thank you.
Yeah.
When you show this desirability, maybe you mentioned it in the main result, is the complexity known?
For?
When you show that it's desirable.
Yeah. No. Yeah. So the complexity could be as high as Ackermann Hart. So because the constant could be as large as possible, right? We don't know that. So at least right now what we have is the constant is like there exists a constant.
And even for the VAS.
Even for the VAS. Yeah, even for the VAS. Because for VAS, basically we use this technique of random amalgamation. Again, you'll get basically this Higman's lemma, and then you'll get this. At least we don't know the best case complexity, but at least there is.
Yeah. So let's thank Kushraj again.
Yeah, am I audible?
So the second talk will be given by Prince Matthew on weighted one deterministic counter automata. Over to you, Prince.
Yeah, good afternoon, everyone. My name is Prince Matthew. I'm a PhD scholar from Indian Institute of Technology, Goa. So today we will be introducing a new model called one deterministic counter automata. So this is a joint work with Dr. Vasu from University of Bodo, Dr. Prakash Saivasan from IMSC, and my supervisor, Dr. Srijit Devi from IIT Goa. So a full version of this paper can be found in archive. You can also find a shorter and longer version of this talk on my webpage. Yeah, so this is the outline of the talk. First, we'll just recollect what one counter automata is, and then we'll introduce the model called one deterministic counter automata. We'll look at the motivation. We'll take a look at an example to understand this model better. We will then take a quick look at our equivalence results, and we'll also look at a reachability problem for ODCA, which is at the heart of solving the equivalence. We'll also take a quick look at what is a one counter automata? You can think of it as a finite state machine with a counter which had access, which reads from a readily one by input type. Okay, so just for the sake of completeness, I'll just share this. The finite state machine can increment the counter, it can decrement the counter, it can choose not to do anything to the counter on reading an alphabet from the input type. It can also test the counter for 0. So ultimately, the finite state machine has two sets of transitions, one for counter value 0 and the other for positive counter value. Right, so this is a one counter automata, and these are the existing results in one counter automata. The equivalence of deterministic OCA is in P. This is proved by Bowman and Gola. In fact, it's in NL. And the equivalence of non-deterministic OCA is undecidable. And the equivalence of weighted OCAs, even if the weights are from a field, is an open problem. So without further delay, let me just introduce the model. It's called one deterministic counter automata. Semantically, you can think of it as a one counter automata, where all the runs of a word lead to the same counter value. So imagine a non-deterministic one counter automata. You can have multiple runs for the same word, right? So irrespective of which run you take, the final the counter value that you reach is going to be a constant for a given word. Okay, so this is a semantic notion. So syntactically, you can think of it as a following model. So you have a counter structure here, you have a counter, and you have a finite state machine. So the counter structure, counter, and the finite state machine, and the input type, together you can think of it as a deterministic one counter automata. So the transitions of the counter structure here are deterministic. So this is the counter structure can test the counter for 0. So essentially test two sets of transition functions, one for counter value 0 and the other for counter value 1. And the counter structure can increment the counter, it can decrement the counter, and it can choose not to do anything to the counter on a transition. The finite state machine here, it cannot alter the contents of the counter. It cannot modify the counter. It can only test for a counter 0 test, right? It can test whether the counter value is 0 or not. So again, the finite state machine here can have two sets of transition, one for counter value 0 and other for positive counter value. And on reading a alphabet from the input type, both the counter structure and the finite state machine can take a transition simultaneously, right? So this is the syntactic definition. We'll take a look at an example and see how it works to understand this model better. So yeah. So consider the example. So this is a function called equal prefix of w. So the function outputs 2 times k, where k is the number of proper prefixes of the word w with equal number of a's and b's, provided for every prefix you have more number of a's than number of b's. Okay, and it outputs 0 otherwise. So I'll give another moment to take a look at it. So the function is equal prefix of w. The function outputs 2 times k, where k is the number of proper prefixes of the word w with equal number of a's and b's. If you have more number of a's than number of b's for every prefix, otherwise it outputs 0. Okay. So this is a function which is recognized using a weighted ODCA. Okay, you can clearly see that this cannot be recognized even using a cross product of a weighted automata or a one counter automata, because we have to, you will understand why. So ODCAs, you can think ODCAs are actually a strict extensions of visibly OCAs, and similarly weighted ODCAs are strict extensions of weighted visibly OCAs. So this is an ODCA recognizing the language that we just saw. Okay, so this is a function which is recognized using a visibly weighted OCA. So on seeing every A, you increment a counter. On seeing every B, you decrement your counter, right? So your counter structure here has only one state. So yeah, and the finite state machine part, you have two states, Q0 and Q1. So you have an initial weight 1 on Q0, and you have an output weight 1 on Q1. Okay. So let's say you look at this transition here, it's marked A02, meaning that this transition can be taken when you read an input letter A from the state Q0, if your counter value is 0 and the weight of this transition is 2. Okay, so similarly, this, if you look at this transition, it's about B plus 1. It means that this transition can be taken on reading a B if your counter value is positive and the weight of the transition is 1. Okay, so yeah. So initially you are in the state Q0 with weight 1 and state Q1 with weight 0. So the current vector, so this is the initial vector. It basically, this denotes the weight in which you are in each of these states. So what happens when you read this? Yeah. So if you look at this transition, look at this finite state machine, you can see that this transition here, it can be taken from Q0 only when you have equal number of A's and B's in your prefix, right? For instance, initially you have epsilon. When you read the first A, you can take this transition because your counter value was 0. So you could take this transition and you could move to Q1. So now we are in state Q0 with weight 1 and state Q1 with weight 2. Okay, and your counter has incremented. The current counter value is 1. So again, on reading the next day, what happens? Your counter value is positive, so you can just take these two transitions here. So your weight vector does not change. Now on reading the next B, you decrement the counter, your counter becomes 1. Again, on reading the next B, you decrement your counter becomes 0. Now on reading the next day, you can see that you can take this transition from Q0 to Q1, and your weight vector becomes 1, 4. Okay, so this process goes on. You read the next B, your counter decrements, your counter again becomes 0. So on reading the last day, you would get this transition and your weight vector becomes 1, 6. So now we have a output weight 1 on Q1. So you will output the weight corresponding to state Q1 here. So the weight with which this word is accepted is 6. You can observe that the word has 3 proper prefixes with equal number of A's and B's. So one is epsilon, one is AABB, and the other one is AABBAB. So I hope this much is clear. So again, instead of looking at this transition, you can also think of the run as multiplication of the transition matrices. So for every input alphabet, you could have 2 sets of transition matrices, one for counter value 0 and the other for a positive counter value. Right, so here A has two transition matrices. Let me call them delta 0 of A and delta plus of B. And B has only one transition function, delta plus of B, because you cannot decrement your counter below 0, right? So you cannot take a transition B from counter value 0. So initially, so this is your initial vector 1, 0. This is your final distribution 0, 1. So given a word W equal to AB, AAB, BABA, the counter value is determined by the input alphabet, since it's a visibly system, right? So you choose whether to take delta 0 of A or delta plus of A based on the current counter value. So for this word, delta of W would be delta 0 of A times delta plus of A times delta plus of B and so on times delta 0 of A. Okay, and the weight with which the word, this word W is accepted would be the initial distribution times delta of W times the final distribution. So yeah, so again, a configuration. So if you look at this example, you can see a configuration of an ODCA here would be this weight vector along with the counter state and the counter value. So if you're talking about the visibly system, we'll just forget about this counter state. So a configuration of a visibly ODCA is just this weight vector and the counter value. So the motivation behind this study. Yeah. So if you think about equivalence of probabilistic push-down automata, this is an open problem. In fact, it's interreducible to multiplicity equivalence of context-free grammars. So what if, even if you try with a single letter input alphabet, this problem is at least as hard as polynomial identity testing. So if you think about, so what about if you restrict the, from a push-down automata, what if you come to one counter automata? But even for probabilistic one counter automata, the equivalence is not to be known. Okay, so the probabilistic ODCAs that we introduce is actually a subclass of probabilistic OCAs for which equivalence is desirable. In fact, we show that this is in P. So this is also a strict superclass of visibly probabilistic OCAs. Actually, our results are a bit more general than visibly because visibly has only one counter state. You could have multiple counter state, and also it's strictly more general than probabilistic because we consider weighted ODCAs where weights come from any field. So these are the equivalence results that we have. The first one would be the equivalence of deterministic ODCAs in P. So a deterministic ODCAs is a ODCA where your finite state machine, the transitions of your finite state machines are deterministic. So for these kinds of machine, the equivalence is in P. So actually deterministic ODCAs are actually equivalent to deterministic OCAs. And from the equivalence results of Baum-Angola for deterministic OCA, you get that the equivalence is actually in P. And for non-deterministic ODCAs, the equivalence is in P space. So if any non-deterministic ODCAs, you can convert into a deterministic ODCA, and a P space machine can check the equivalence. So our main results is that of equivalence of weighted ODCA. So when you have a weighted automaton, if your transitions are weighted, so we show that equivalence of weighted ODCAs is in P if the weights come from a field. So ultimately, how we do this, we reduce it to an equivalence problem of a weighted automata for of a big weighted automata, and then we prove the equivalence of, and we show that the equivalence can be checked in polynomial time. So since you get a polynomial size weighted automata, the equivalence of weighted automata can be checked in a polynomial time. So how do we prove equivalence? So at the heart of solving the equivalence, there is a reachability problem. So we will just introduce the reachability problem as an independent problem and tell how it is being solved. So for the reachability problem, okay, for the rest of the talk, we'll assume that what we have is a visibly weighted system. So you don't have to worry about the counter structure states, right? So even if for the general case, you can extend this idea by just including a counting argument. So our input is a weighted visibly OCA, and you are given with an initial configuration C. You are given with a vector space V with some proper basis, and you are given with a counter value M. So what is the reachability question? The question is, from the configuration C, can I reach a configuration whose weight vector is in a given the complement of this vector space and whose counter value is M? Okay, so we should output S if there is such a run. We should output no other. Okay. So we call Z a reachability witness if from C you can take this set and reach a configuration whose vector is in the complement of this vector space and whose counter value is M. Now, yeah. So we were able to prove that this Covius reachability is actually desirable in polynomial time. So how it is solved? It is solved using by solving a pseudo pumping lemma. So what is this pseudo pumping lemma? Yeah. So here you can say see that there is a reachability witness from configuration C to yeah. So you have a reachability witness for the configuration which is in V bar cross M from configuration C. So assume that the maximum counter value encountered during this run is greater than some polynomial bound. Then essentially what this pseudo pumping lemma is saying that you can cut this portion out to get a shorter witness of reachability, and the maximum counter value encountered during this run is smaller than what you had before. So in the case of non-weighted, like one counter automata, showing such a property was really easy because you just had to look at straight repetitions and then you could find this easily. But now you are dealing with vectors and you have to ensure that even after removing portions from either side, you have to ensure that you reach the same complement of the vector space. So we use some linear algebra to prove this. I'll just give a quick proof idea. So assume that you start from configuration X here, a configuration with weight vector X and counter value 0, and you reach a configuration here, which is in V bar. Okay. So so I look at the transition matrix of the word, which takes me from counter value 0 here to counter value 0 here. Right? Let me call that matrix M9. I know that, so I initialize A9 and B9 to be some identity matrices. I know that X times I times M9 times B9 is in V bar. Okay, so this is the initial assumption. Now, again, I look at the transition matrix of the word, which takes me from counter value 0 to counter value 1 here. Okay, and I name it A8. And M8 is a transition matrix corresponding to the word, which takes me from counter value 1 here to counter value 1 here. And B8 is a transition matrix corresponding to the word, which takes me from counter value 1 to counter value 0. Right? Again, X times A8 times M8 times B8 is in V bar. So essentially, it's the same multiplication taken in a different order. So I repeatedly do this. I have A7 here, A7 X times A7 times M7 times B7 is in V bar. X A6 M6 B6 is in V bar, and so on and so forth. And I get that, yeah, X A0 M0 B0 is in V bar, right? So now what I do, I'll just list these matrices M0 to M9 here. Okay. So I assume for the time being that these MIs are 3 by 3 matrices. So for all I know that XAI, MI, BI is in V bar. So I get that there exists an MJ, which is a linear combination of everything before it. So since let's say your MI is a 3 by 3 matrix, if you look at it as a vector of size 9, you can only have, let's say, 9 independent vectors of size 9. So since you have 10 vectors, 10 matrices here, one of it has to be a linear combination of everything before it. So there exists an MJ which is a linear combination of everything before it. So yeah, so I just substitute that and I get XAJ times this linear combination times BJ is in V bar. Now the claim is that there exists a K which is in 0 to J minus 1 such that XAJ MK BJ is in V bar. So why is this true? Assume that this is not true, that XAJ MK BJ is in V for all Ks, then this is nothing but a combination of stuff which are already in a vector space, and it contradicts that this is in V bar. So there should exist a K in 0 to J minus 1 such that XAJ MK BJ is in V bar. So for the time being, let's assume that my J here is 6 and my K here is 2. So what I can do, I know that X times A6 times M2 times B6 is in V bar. So I replace M6 by M2 and hence get a shorter witness of reachability. So you can observe just by the pseudo pumping lemma, you can bound the maximum counter value encountered during the reachability witness. And hence, yeah, so if you have a run like this, you can apply the pseudo pumping lemma in each of these portion and bound the maximum counter value encountered during the whole run. So with this, you can actually show that the reachability is in P, because now this is just a reachability, since the maximum counter value is bounded, this is just a reachability problem of a weighted automata. So you can do it in P time. So now we have a special word lemma. So why the special word lemma? So this is special word lemma is similar, says that if you have a reachability witness, it has some canonical form, right? So this is similar to what Weylian had for deterministic one-counter automata. And it was actually at the heart of solving the equivalence of deterministic real-time one-counter automata. So Bowman and Kohler were able to utilize this to prove the equivalence of deterministic real-time one-counter automata. So what this special word lemma says, it says that the lexicographically minimal reachability witness has a special form. It's of the form U y1 raised to R1 W1 y2 raised to R2 W2, says that U y1 W1 y2 W2 is polybounded, and R1 and R2 are also polybounded. Okay. So again, for one-counter automata, this was easy to show. You just had to show that you can just pump out some portion and then repeatedly pump some portion in to get a canonical form. But now, since we are dealing with vectors, this is intrinsically more difficult to do. Now, how do we prove this? Let's say I start from a configuration with counter value n, and my weight vector is x, and I reach a configuration here with counter value m. So I mark the points where I encounter, let's say, counter value n minus I here, and I mark the point where I encounter counter value n minus I minus d here, right? So I call the word xi, which takes me from counter value n minus I to counter value n minus I minus d, right? So what we claim, the first claim is that if this d is large enough, there is a very large factor which repeats in my lexicography minimal reachability witness. So if I just plot those points, let's say I start from here x, I reach, let's say, counter value 0, and x a0, m0, b0 is in V bar. So, okay. So what is a0? A0 is identity. M0 is a transition matrix which takes me from counter value 50 to, let's say, counter value 9. B0 is a transition matrix of the word which takes me from counter value 9 to counter value 0. Right? So I know that x a0, m0, b0 is in V bar. So again, A1 is a transition matrix corresponding to the word which takes me from counter value 50 to 49. M1 is a transition matrix corresponding to the word x1 which takes me from counter value 49 to counter value 8. And B1 is the transition matrix corresponding to the word which takes me from counter value 8 to counter value 0. So I do this, I again know x a1, m1, b1 is in V bar, x a2, m2, b2 is in V bar, so on and so forth. And I get, yeah, x a8, m8, b8 is also is in V bar. So now we apply an argument similar to what we did for pseudo pumping lemma. If you just, again, we assume that MAs are 3 by 3 matrices. Now you arrange the words x0 to x9 in the length lexicographical order. So let's say this is the ordering, xi0 less than xi1 less than ... less xi7. Now we apply a similar claim. We know that for all j, x, aij, mij, bij is in V bar. So there exists some j here, which is a linear combination of everything before it. So the same argument we make. So basically you get there exists a k in 0, j minus 1 such that x, aij, bik, and bij is in V bar. So let's say this k is 2. It means that I could have replaced mi7 here with mi2. Essentially, I could have replaced xi7 with xi2. But this means since xi2 is a lexicographically smaller word than xi7, it would contradict the minimality of my reachability witness. So this cannot be done. So what this essentially means is that if I look at my minimal reachability witness, there is a very large factor x which repeats in the minimal reachability witness. So let's say my reachability witness is z. I can write z as u1x w1. I can also write z as u2x w2. Okay, so let me just call this portion v. So here, this v is a prefix of x. So v has to be a prefix of x here as well. Now, these two portions are essentially the same portions of the same word. So this is also v. Now you get that vv is a prefix of x. So vv is a prefix of x here as well. You could continue doing this till the end of the word, right? So, and hence you get the special form. So now your word is of the form u1 v raised to r1 w1. Okay. And it's easy to show that this v1, u1, and w1 are polybounded. Now, if you have a run like this, you can show that this portion is of the form v1, like u1, v1 raised to r1 w1. This is of the form some u2, v2 raised to r2 w2, and this portion is also polynomially bounded, and hence giving you the canonical form. So with this special form and the pseudo pumping lemma, you can adapt the proof techniques by Bohm and Guller for deterministic real-time one-count automata, and show that this equivalence is actually doable in polynomial time. So how is it done? So basically, the idea is that you bound the maximum counter value encoder during the run of the minimal witness, which distinguishes these two machines, and you just then construct a weighted automata to check the non-equivalence. And this can be done in polynomial time if the weights are from a field. So so another result is regularity. So this is a problem of determining whether a given weighted ODCA is equivalent to is there a weighted automata recognizing the same function. So regularity is also in P is another result. So how so the crucial idea here is that, again, like pseudo pumping lemma, here you have instead of pumping down, there's a pumping up. We show that if there is a witness from this configuration here to a configuration here, and the maximum counter value encountered during the run is greater than some polynomial bound, then essentially what we show is that you can pump this portion up to get a larger witness of reachability whose maximum counter value encountered was greater than before. Right? Essentially, what you do here is that you show the existence of infinitely many equivalence classes and hence a non-regularity. Yeah, so these are the main results that we have. It's the equivalence of weighted OCAs is in P if the weights non-map field, and regularity of weighted ODCAs is in P. So these are the existing results in the non-weighted and weighted setting. So for probabilistic automata, we know that the equivalence is in P. For deterministic weighted real-time uncounted automata, the equivalence is in P. So this is a corollary of our result. For weighted ODCA, the equivalence is in P. Again, this is our result. So the future direction would be to look at deterministic stack push-on automata, where the stack operations are deterministic, and probabilistic push-on automata. So these are still open problems. So one can also look at active learning of these machines as well. Since the equivalence is desirable, a possible future direction is also to look at the active learning. So these are some references. Yeah, thank you.
Thank you, Prince. Questions? I have a couple of questions. So you initially you said you had that example of 2K prefixes. You said that it was not possible to do it with some other things. Which were those other things and why was it not possible?
So basically, I just said that it cannot be done using a product of weighted automata and a one-count automata. Because if you, okay, let me just go back. So basically, the weight on the transition on that A when the counter value is 0, right? So the weight on the transition was actually dependent on the counter value. So if you had your weight and the counter separate, there is no way of testing for a counter value 0.
So this is one deterministic because in every run, the value was actually 2. That is why it was one deterministic.
Okay, could you?
Your machine was one deterministic, the thing that you gave, because in every run, the value was 2. That was the definition of one deterministic,
The
right?
counter value for every run is constant, is fixed.
Counter
So
value.
any word you take, so let's say your word might have, let's say 5 runs.
So the counter behaves exactly the same in all the
runs,
different runs.
Yeah, so that's some notion.
Okay, it has nothing to do with the weight.
It has nothing to do with the weight. Yeah. So the weighted, it can be, yeah, transition.
Okay.
What would we do in the case, so in the pseudo pumping lemma's proof, we assume that, well, the counter's max value is sufficiently large that you can get this linear dependence result.
Yeah.
What do you do if that's not the case?
So if you're saying if the maximum counter value is smaller than a bound.
Yes, smaller than like
So
the
what
size.
you could do then, essentially what you're saying is that the minimal reachability witness, the run of the minimal reachability witness,
Yes.
the maximum counter value is already polybounded, right?
Okay. So
And
in
then
that
you
case,
could just unfold the one count automata to get a big weighted automata and then check the
I see.
reachability.
Okay. Okay. Yes.
So in this question that you showed, open questions, you had this whatever deterministic push down. Does it mean that in every non-deterministic run, the stack is exactly the same?
The stack is exactly the same. So there is another version where where the people consider high determinism. It means the stack height is fixed in every run.
Okay.
So, but this is a more restrictive.
So this is also like studied.
So deterministic stack push on automatas were studied. Yeah. So deterministic.
Deterministic stack.
Yeah. So
Deterministic height.
Deterministic height push on weighted visibly push on automatas were studied, and I think Stefan Kiefer has a result saying that it's in co-RP. The equivalence is in co-RP, and there's a polynomial time reduction from PIT, so it's unlikely to be in P.
So, thank you, Prince.
Thank you.
We have a short break now, and then we have the business meeting. All of you are welcome to attend the business meeting. Okay, everybody who is interested in IARCs, FSTTCS, and in this community are welcome. Sign something. You cannot leave. You ended early. You did not end early. For me, it was already 4:30. I was trying to end. I did not arrive.
It was not.
One more question, which I will ask later.